Check.
Thank you. So can you see my slides?
Yes, we can.
Yes.
Okay.
Yes.
Thank you. Well, hello, and thank you for giving me the opportunity to talk today. I'm going to speak about several aspects of a phase of gauge theories known as partial deconfinement, based on these two papers. So I hope to show you that it's a very rich and interesting area of study. And I'll mention now that the terms partial confinement and partial deconfinement mean the same thing, and I'll use both terms interchangeably. So this is the roadmap for my talk. First, I'll tell you, give some motivation for studying partial confinement. Then I'll tell you about some things which have been known for a long time about regular confinement. Then I'll give an overview of what was known about partial confinement until before the work that I'm going to present today. Next, I'll tell you about some dynamical aspects and interaction between particles in partial confinement. Fifth, I'll talk about how global symmetries relate to partial confinement. And then finally, I'll say a bit about how partial confinement relates to holography and QCD. Okay, so first, why should we be interested in partial confinement? So we want to understand QCD in the real world, especially the quark gluon plasma. So the quark gluon plasma and the phase diagram of QCD aren't currently well understood, and a lot remains conjecture. But they're very important areas of study. So, for example, the quark gluon plasma is very important in cosmological history, as it dominated the universe for some period of microseconds after the Big Bang, and the rest of cosmological history is influenced by this time period. Also, something like the quark gluon plasma appears in heavy ion colliders, such as RIC at the Brookhaven National Laboratory, and at the LHC they have ALES. And we claim that we'll need to know about partial confinement in order to understand these. Partial deconfinement is also a property of gauge theories in general, and it will be important to the task of understanding gauge theories at strong coupling. And finally, gauge gravity duality. So for every phase in field theory in a given duality, there's a joule in the gravity theory, and we want to know what's the joule of partial confinement. So I have more to say about each of these at the end of my talk. But in particular, we think that we can learn about the thermodynamics of black holes by exploring partial confinement on the gauge theory side. So next, I'll tell you some basic facts about confinement that have been known for a long time. So first, I have to cover some even more basic things, such as how to introduce a temperature to a quantum field theory. So this is the partition function, which governs all things in the thermal theory. Beta is 1 over temperature. And we want to know how to compute this. And there's a way of doing this by modifying the standard path integral of quantum field theory. So first, we Rick rotate by taking time to be imaginary. And we say that we're in Euclidean time, since according to the metric, the time direction now behaves the same way as the spatial directions. And if we take the length of the time to be beta, then the final expression that we get from this path integral will look like the thermal partition function. And then next, if we impose periodic boundary conditions for the bosonic fields, then this acts as the trace, and the final expression will look like the thermal partition function. Should also note that it would be useful for later that if you follow the same procedure for fermions, then you have to impose anti-periodic boundary conditions. But the conclusion is that if we can introduce a temperature into a field theory at equilibrium by taking our standard quantum field theory, quick rotating, and then compactifying on this Euclidean time, and where the scale of the compactification scale is inversely proportional to the temperature, and so we call that beta. Also, for any discussion of gauge theories, we'll need the Wilson loop. So this is how it's defined. P is the path ordering operator, and the trace is taken over the colors, the color indices, and it can be taken in any representation of the gauge group labeled by R. And this is just the trace of the holonomy, and it provides the gauge invariant observable. And this is important because gauge symmetry is just a redundancy, so any physical quantities must be gauge invariant. When we don't specify R, then we take it to be the fundamental representation. And there's another way of thinking about the Wilson loop. So the expression for inserting a very massive quark is given by this, which is the same as the Wilson loop. So we can think of the Wilson loop as inserting a very massive non-dynamical quark and constraining it to follow the path C. And this would be a useful perspective for us later too. The third basic concept is the Polyakov loop. So this is actually just a special Wilson loop, but it's so crucial to the story of confinement that it deserves its own name. It's just the Wilson loop taken over the temperature direction, and we use the same Wilson loop definition here. But however, it would also be very useful to consider this object, this P here, which is the holonomy before we take the trace over the gauge indices. The most convenient way to think about this object is by diagonalizing it and then taking the eigenvalues. So, and if you look at this expression, you can see that the eigenvalues will all be phasors. So it's often convenient to represent them, these eigenvalues on a circle here. So this encodes the holonomy and the Polyakov loop before tracing.
So one question. So just a qualitative question. So why are the eigenvalues of the Polyakov loop, let's say, emphasized as opposed to the Wilson loop? Is it?
It's just because later in the talk we'll be making a lot of use of these eigenvalues.
Yeah.
So we just don't need them.
So the reason why we are doing that is like as some sort of order parameter for confinement, that kind of thing. That's the reason why we are introducing it, or?
Yes. So okay. I'll show that later, but yes. Also, you'll be able to see things like center symmetry much more easily using these eigenvalues. Okay.
My question is actually kind of naive in the sense that, like in principle, one could diagonalize a general Wilson line operator also, right?
Yes.
Okay, yeah.
It's just that that's not so useful to us as doing this for the Polyakov loop.
Yeah, thanks.
Okay. So finally, we can talk about confinement itself. So the word confinement comes from the observed fact that you can't isolate single quarks, but they're always found bound with other quarks or antiquarks, and confined within composite particles. And the reason for this seems to be due to the formation of flux tubes between quarks and antiquarks. Flux tubes are the most interesting and distinctive property of the standard confined phase. And when you place a quark and an antiquark in the theory, a tube of chromoelectric flux forms between them. This tube is made out of the gluon field, and they were first proposed theoretically, and now they appear in simulations like this one from the University of Adelaide. And in what follows, I'm going to assume that there's no fundamental matter in our theory. So what I'm about to say about flux tubes doesn't apply to QCD, and it's easiest perhaps just to think of a pure Yang-Mills theory, and I'll explain how this relates to QCD later. So because these gluon and force fields remain concentrated in this tube, the potential doesn't dissipate, and by Gauss's law must increase linearly with the separation of the quark and antiquark.
So the simulation that you showed from Adelaide, the one that you showed with the red color and all that. So that one,
yes.
is it a real-time simulation, or what is
it? I think this is a still from a real-time simulation.
So it's not like Euclidean lattice gauge theory. It is really like you're seeing the dynamics of flux tubes.
Yes.
Okay. Cool. So can you say one or two words about what do they do? I mean, what makes real-time physics accessible?
I don't know much about this because I was just talking about
okay, fine. Generally, like typically in lattice gauge theory, for instance, one hears this thing that you can understand the phases but not the dynamics of QCD typically, right? I mean, largely because I mean, thermal, Euclidean signature is more amenable to Euclidean physics and so on. So here it looks like from the picture itself, it looks like something dynamical is happening. That's why I thought I'll ask that question. So yeah. Anyway, yeah. Thanks.
Yes, I just put this in here to try and demonstrate this nice flux tube. Okay, so have in your mind pure Yang-Mills for what I'm about to tell you. Yes, okay, so the energy just decreases indefinitely as you increase the separation, and it takes an infinite amount of energy to separate the pair. And this is what's responsible for confinement. And it's characteristic of confinement that the potential grows linearly. In contrast, in a deconfining phase, they don't have this concentration of flux, and the potential drops off as you separate them, and you can treat them as if they're independent particles. So, for example, in the Coulomb, you get a 1/L drop off if it's in 4 dimensions. But we need a precise and gauge invariant way of defining this property of flux tubes and the linear potential, and it's standard to use the growth rate of a Wilson loop that's taken to be infinitely large. So we can use the Wilson loops to give evidence about the partially confined phase later as well. So as I said earlier, the Wilson loop in the fundamental representation can be thought of as an insertion of very heavy non-dynamical quarks taken along some specified curve C. And so for simplicity, we'll take the C to be a rectangle, and we can construct the path in the operator formalism as follows. First, we create the quark anti-quark pair at one instant in time with the operator f dagger, and then next we propagate it in Euclidean time tau for a very large tau. We take tau to be large that only the lowest energy state will dominate, and then finally we annihilate them. And therefore, an expression for the Wilson loop in the operator formalism is this. And the key point is to look at the Hamiltonian. Since the quarks are non-dynamical, it corresponds to the potential created by the quark anti-quark pair. And if we have the special property that the potential is linear, then the exponent corresponds to the area of the path C, and this easily generalizes to different shapes of loops, as you can just combine rectangles. And because it's constructed from a Wilson loop, it's a gauge invariant and precise statement. So this is a precise way of encoding that the potential is linear.
What is F here?
F is the creation operator for a pair of quark and antiquarks. Okay, so at finite temperature, sometimes this doesn't work well, because if the temperature is high, then there's not enough space to take a large rectangle in the temperature direction. So we do this instead. We can follow the same logic as before, and we'll see that this Wilson loop gives an area law. But it's easier to think of this as the correlator of two Polyakov loops. So you can see these are Wilson loops which have been taken around the thermal direction, so they're Polyakov loops. Then the potential between these loops involves the potential between quark and antiquark pair, but as well as containing the factor of the temperature or the inverse temperature. And this is just like the area law expression for if B is linear.
Sorry, can you just flash your previous slide for one more second? I just wanted to take a look. The one before this.
This one.
Yes. So so in your new picture, so this so the idea is that the vertical direction you want to take it to be as large as possible in some sense. Is that correct?
Yes.
And that's not possible when you're in a Euclidean circle because the size of the circle is finite.
That's right.
So that's okay. So I see. So instead, what you do is you just bring it back to wherever you came from, and then so you just go around once. Is that the idea?
Yes. So yeah. So these you could think of these P daggers as being like the F daggers in this previous picture, in a sense. Yeah. But they're taken as far as you can, and it just becomes easier to think of them as Polyakov loops instead.
Yeah.
Okay. So it might seem unhelpful that we have this remaining parameter L, and we can often get rid of parameters like this by taking them to an extreme, like L to infinity. And if we do that here, then we find something interesting. So we take this separation to be infinite, and so this expression should factorize by cluster decomposition, since each Polyakov loop should be independent. And combining this fact with the fact that it has a linear potential, then we can deduce this property about a single Polyakov loop. So we can think of the single Polyakov loop as being an insertion of a single quark, and now we can think of it as coming combined with a free energy for inserting that quark, and so F is the free energy cost of inserting the quark. In a confining theory, then we don't have independent quarks, so we would expect that the free energy cost to be infinite. In which case, we would get value for the expectation value of this Polyakov loop of 0. In contrast, in a deconfining theory, we would expect the potential and the free energy cost to be finite, and so the expectation value of P would be finite. So therefore, it looks like taking a single Polyakov loop is an order parameter for confinement. So let's investigate this a bit more and see what symmetry this order parameter might be associated with. So we again express the holonomy in terms of eigenvalues. If the expectation value P is equal to 0, then the eigenvalues must have a shape like this, and the symmetry is manifest. There's a shift symmetry on the eigenvalues, and if we multiply, the action is by this for SUN. Then we have this symmetry, and this Zn coincides with the center of the gauge group, since the phases are abelian. So we call this center symmetry.
Sorry, I kind of missed the point. So why is it that so this picture is basically denoting the location of the faces, I guess, right?
Yes.
So why is it that the sum has to vanish necessarily mean that it is e to the pi I by n? I didn't see that.
So it's in this expression here. So
yeah. I mean, in principle, they could be distributed in some way so that the sum kind of becomes 0. I mean, it's right. I mean, does it have to be on the? It seemed like you were saying that it has to have a symmetry, a Zn symmetry. So I'm not. That's the.
Yes. So if you inserted sorry. Maybe I'll show you the next slide then. So yeah, so well, it's a consequence that if this property holds, then this the Polyakov loop holonomy P will be symmetric under this action.
Okay, so yeah, I guess what you're saying is that I see. It's not a statement about the location of the things, but I guess it's a statement about the fact that if you have a shift symmetry in the faces of each of those things. Is that the statement?
Yes.
Okay. So okay, so that there is a center symmetry. Yeah, that's okay. Thanks.
Okay. So this in a more general case, then in the deconfined case, then you wouldn't have this center symmetry of the eigenvalues. So we can conclude that center symmetry is a signature of confinement, and incidentally, I can mention it's a one-form symmetry, and so the charge acts, the polygon groups charged under this action of this symmetry group. So this then means I can tell you why QCD is different. And recall up to now that we've been thinking of a theory like pure Yang-Mills without fundamental matter. But in QCD, as you separate a quark-antiquark pair, the energy can become high enough for a new quark-antiquark pair to be created from the vacuum. And these flux tubes are then limited in length, and they stop scaling linearly with the separation L between the original quarks, or the original quark and antiquark. And the essential reason for this is that dynamical fundamental matter, like quarks in QCD, break the center symmetry. The reason flux tubes can form indefinitely in pure Yang-Mills is because they're protected by the center symmetry. And this means that neither the Wilson loop nor the Polyakov loop characterizations of confinement work in QCD. But they're very useful in pure Yang-Mills, and confinement seems to be driven by the result of the action of the gauge fields. This is why it's worth looking at pure Yang-Mills. So to summarize, in confinement, confinement can always be characterized by the absence of single quarks, and this works in QCD. And instead, we always have some color singlet bound state. And also by the formation of flux tubes of some size. But in pure Yang-Mills, we can also make these statements that we expect to have linear potential, an area law for the Wilson loop, and central symmetry where the Polyakov loop is the order parameter. So now I'll tell you about what the state of the art in partial confinement was before the new work I'm going to introduce in this talk. And everything in this theory depends not only on having matter and having theories about fundamental matter, but also on being the large N limit. So the large N limit is quite a strong constraint, and the new work I'll show later will tell us how to move to the finite N. But for now, it's easier to imagine something like UN or SUM pure Yang-Mills. So I'll begin with a cartoon of what partial confinement is. So we essentially mean that a subgroup of the gauge group deconfines, and that means that adjoint matter like gluons will look like this matrix, where M is the number of deconfined colors and N is the total number of colors. And we expect actually that an SUM gauge group, a subgroup of the original SUN is deconfined, and then an SUN minus M subgroup is confined. And for fundamental matter like quarks, we would have a situation shown by this vector where M entry is deconfined. But as I said, we're not going to think about fundamental matter for now. And this situation was first articulated by Hanada and Maltz in 2016 and David Berenstein in 2018 in these papers. But that was just a cartoon. So let's look at a specific gauge invariant object, and we'll take the Polyakov loop before the trace again. This gives us a matrix, and we can express it again in terms of the eigenvalues. And because we're in the large N limit, it will also be very useful for to us to think of the density of eigenvalues. So in the confined case, we've looked at that the eigenvalues would be distributed like this, and the eigenvalue density would be uniform. In a deconfined phase, the eigenvalues have a more general distribution without any center symmetry component, and the eigenvalue distribution at large n would look like this, where it's gapped at the edges, and it's 0 along here. So that takes us to the partially confined phase. And here we expect some of the eigenvalues will have center symmetry, like these green ones, and others will be deconfined and not have center symmetry. And that would lead us to the eigenvalue distribution, which looks like this. So
is that sort of the working definition of partial deconfinement?
Yes, this is the definition that people often started with, but it only works at large n.
Yeah. But I mean, in principle, this sort of a definition can work at finite n also, right? I mean, this center symmetry based definition that you just made.
Yes, this part can work at finite n. The eigenvalue density, this part isn't precise at finite.
No, but my question was like, partial deconfinement seems like a, sufficiently sort of mysterious idea. I mean, at least in the case of deconfinement, in full deconfinement or confinement, you kind of have like some intuitive notion of what it is. But here, so I'm asking basically what is sort of the operational definition of partial deconfinement? Is it that there is partial center symmetry present? Is that the definition?
Yes. So if you're willing to talk about gauge symmetries, then you could say that there's this like the SUM and the SUN minus M groups. Some people aren't willing to talk about gauge symmetries, in which case a more precise definition seems to be in terms of these eigenvalue distributions at large n.
I mean, what is wrong with the, I mean, so some people are not willing, I mean, I guess it's a question of you want to have a gauge invariant definition of what partial deconfinement is. Is that what you mean?
That's right, yeah.
So, but even by that standard, it seems to me that like somehow having something like a, Polyakov loop having being in a partially center symmetry broken phase, it's still well defined, right? If you have a theory which has n and m are well defined quantities, even if you, aren't they?
Well, this in this case, the Zn center group is actually physical, but Zm a subset. That's just the gauge. So
yeah, you're right. Yeah, okay, yeah. So it's okay. So it's not very clear. So I guess the punchline sometimes it's not super clear what exactly partial deconfinement is. Is that a fair statement?
I guess so.
At finite n, at large n. Yeah, that's right. So the point, I guess, is that the eigenvalue distributions are. So why do you say that at large n it is well defined?
Well, because at large n this is actually a continuum, and and in the large n limit, then we can actually say that these edges formally go to 0. But if we're in finite n, then there's actually always a finite component in this area.
Okay, I see. Yeah. Thank you.
Okay. So given what I just said, this component of the eigenvalue distribution should correspond to the amount of the gauge group which is confined or deconfined, and so you'd expect to be able to perhaps read off the value of m from here, and that's what we find. This height is proportional to 1 minus m over n. So m is the amount of number of colors which are deconfined, So if they're all deconfined, then m is equal to n, and we have 0 here. If they're all confined, then m is equal to 0, and then this is 1, and you'd expect the whole distribution to be 1 in this normalization. And also, given the previous slides, it's clear that the critical point is the transition between the deconfined and the partially confined phase. It's when this eigenvalue distribution becomes ungapped, so where there's no longer any zero density, and we call this the Gross-Witten-Woddier transition, in analogy to work that was done on the 2D lattice, which showed similar behavior in the eigenvalue distributions. So the Gross-Witten-Woddier point will be a crucial focus for us. But again, this is only precise at large n. It's only at large n that this is truly 0 in the large n limit. So before I go on to discuss,
I got confused about which one is the one that you're calling gap, the one on the partially confined phase or the deconfined phase?
This one's gapped, deconfined.
So it's basically the gap.
Refers to this
yeah.
bit.
Okay. I see. Okay, thanks.
So before we go on to discuss new work, there's a couple of natural questions that might have occurred. So one natural question might be, why does the entire SUM subgroup deconfine rather than something more arbitrary without the symmetry? And the answer is actually bosonic interference, and it works for the same reason that a condensate forms in the Bose-Einstein condensate. So in a Bose-Einstein condensate, bosonic particles are identical, and they have a redundancy or a gauge symmetry under permutation of the particles. If a set of particles are in different energy levels, then labeling them is highly redundant, and we can project out to get a gauge invariant state. We must correct for the overcounting, like this. So there are 6 labels which refer to the same state. But if particles are in the same energy level, then there's no such redundancy to account for, because the label describes the state already. And this means that there's a relative enhancement of the occupation of this state above others. So it's enhanced by having the S3 permutation symmetry in the gauge extended Hilbert space. So this effect becomes very large when you take a large n, and the result of this is that in the Bose-Einstein condensate, this SU n-m subgroup is highly favored in the ground state, and the case is entirely analogous for the partially confined phase, where you can think of the confined phase as being like the ground state in the Bose-Einstein condensate, and the SU n-m gauge subgroup is enhanced.
Sorry, I got confused. I would have thought that in the SN case that you had, like the if there are n particles, it'll be most favorable for all the particles to be in the ground state, right?
Yes, but then you introduce a finite temperature, and so you have these thermodynamic issues.
True, yeah. So, but I think there is a big difference there, because I think this SN is not gauged in typical bosonic systems, right? Where there is bosonic, this what is it? This Bose-Einstein condensation. But in the case of SUN, like you were saying before, it's like it's a gauge theory, so it's not so clear whether temperature can,
Well, I think you can think of this SN as a gauge symmetry because it's related to the particles being identical. So if you take an ensemble of bosons, then there's a redundancy in the labels, and so it's this redundancy in the labels which I'm referring to as a gauge symmetry here.
I see. So okay, so yeah, okay, thank you. Yeah.
Okay, and another question might be why the upper left block, and the answer here is just we choose gauge fixing, so that we move this block to the upper left. And I'll skip the details of this, but so a typical gauge theory diagram will look like one of these. These are the two logical possibilities. On the y-axis, I'm showing the product of expectation value, but it's related to the energy of the quark, like this expression that I showed before. So you can really think of the y-axis as being the energy. So pure Yang mills would look like this case. This describes the first order transition, where at some point, as you increase the temperature, the free energy of the deconfined saddle becomes lower than that of the confined saddle, and so there's a first order jump between these two saddles. But connecting them we claim as the partially confined saddle, which is always unfavored because it has a negative heat capacity. And so that's perhaps the reason why partial confinement's been ignored for so long. And on the right, we think this is what you'd expect for something like QCD. And in this case, the partially confined phase has been ignored just because it's very hard to investigate QCD. And we think that we can learn a lot about this diagram by investigating the diagram on the left. So this is the confined phase, deconfined phase, and partial in between them. So remaining questions which I'll address next are, what about the dynamics, the flux tubes, and the potentials in the partially confined phase? Everything's been kinematic so far. What about order parameters and symmetries? And what about taking to finite n, since everything's been at large n so far? So I'll talk about these now. This fourth section, dynamics and flux tubes. We'll pick a particular instantiation or particular theory to look at, and we'll look at this UN pure Yang mills at large n strong coupling. You know, so the reason why we picked this theory is really for the convenience of simulation, and because it will tell us a lot about the pure theory as well. So we choose large n so that we can do something called a Gucci-Kawai reduction on the lattice, which means that we can reduce to a single lattice site, which is very useful for computation. And by strong coupling, we mean that we drop magnetic terms in the lattice formulation. So this is just the action familiar for large n UN Yang mills, and here we put it on the lattice with a gauge fixing term, and the length of the lattice is denoted by A. So the phase diagram for this theory looks like this with the unstable partial saddle, and we need to know how to probe this this partial saddle numerically. So normally in the ground canonical picture, we fix a certain temperature, and then the system will jump into whichever saddle has the lowest free energy. But we want to be able to probe this partial saddle. So to do that, we add a fixing term, a large cost to the action, and by changing this this value, then we can probe different areas along the saddle. So first we'll check that this works to the fully confined phase. In the lattice we construct this Wilson loop or correlator of the Polyakov loops that I introduced before, and we should be able to find out whether there's a linear potential between those two quarks. We have an analytic expression for this, which would take to be 1.724. So that's the number to compare our simulations against. So we'll just check this now. Here we've plotted on a logarithmic y-axis the Wilson loop, and against the lattice spacing L.
How did you get the analytic expression, that 0.29 or whatever? How was that? Where did that come from?
So this comes from just the normalization of the lattice that you can do.
So that's a
find
lattice
set
result.
larger.
That's a lattice result, is it?
No, it's analytic.
But how? So how did? So can you repeat what you said?
Yes. So well, you can you can do this. It's simpler to do this at large n. So it uses large n results, I think.
Oh, I see. So these are results that you compute in large n using, for instance, do you use matrix models or something like that? Oh, so this is the Iguchi-Kawai reduction you mentioned. Is that correct?
Yes. Yeah. Well, the Iguchi-Kawai reduction is a way to just place the lattice on a single site.
All right.
I see that I'm running quite late, so I better rush through maybe.
I mean, okay, our time bounds are not very strict, so it's okay. Anyway, go ahead.
Okay. So thank you. Okay, so the point is that this this gradient is proportional to the potential. So because it's linear, then that means that that implies that the potential is linear. And we can compare the exact values, and the fully confined phase is just what we would expect. It's within the error bound. This is the error in the last two digits. So the partially confined phase, we conjecture that the confined subsector and the deconfined subsector behave differently. And so we want a way of being able to probe the different sectors. And the way we do that is as follows. So we take the Polyakov, the holonomy, the Polyakov loop before tracing, and we take the eigenvalues and then we separate it into a deconfined part and a confined part, and basically project onto the different sectors. So in the deconfined part, we take zeros in the confined sector, and for the confined part, we take zeros for the deconfined sector. And so our conjecture would be, after doing this, that the confined part will show flux tubes and a linear potential, while the deconfined part will show something which is sublinear, something like Coulomb phase or Higgs phase potentials. And furthermore, if the confined sector behaves exactly like the fully confined sector, except for the number of colors being different, then we would just expect this factor of difference. So in our other plots, we can change the y-axis by accounting for this factor, and then we would again expect this quantity 1.724 for the gradient. So we'll test that now. So we first fix a value for the Polyakov expectation value of 0.2, which gives a ratio of the deconfined phase to the total phase of about half. And we see that the confined sector indeed has a linear fall off, which suggests flux tubes. And the gradient agrees with our expectation in the theory. So we can check the deconfined subsector too, and see that there's no such linear fall off. So in this case, our conjecture would seem to hold. And we can do the same for a different value of fixing the Polyakov loop. Here, m over n has a different ratio, closer to 0.6. And again, we see this the linear potential for the confined subsector with a gradient which agrees with our predictions. And then the deconfined sector again doesn't have a linear potential. A natural question to ask would be about the mixed correlator. What if we create a particle in the confined sector and then have a Polyakov loop in the deconfined sector? And we would say that we assume that this deconfined operator overlaps with the lightest mode created by this p-dagger con, in which case we would conclude that the we again have an aerial, or that the potential is linear, and so this is what we find at both values of P that we looked at before, and the accounting for the number of colors again, we again get these the gradients which agree with the theoretical result. So this is our conclusion, that in the confined sector we get flux tubes, and in the deconfined sector we get something with deconfining behavior. So that was the new work on the dynamics and flux tubes, and now we'll talk about global symmetries and order parameters and how they relate to partial phase. So previously we knew that the completely confined phase could be distinguished from the deconfined phase by center symmetry, and we want to know if there's something analogous for the partially confined phase. So we'll pay particular attention to this point here, which is when the deconfined saddle turns into the partial saddle. So we already know around here that we expect center symmetry to be broken. So we have to turn our attention and see if there's any symmetry which breaks here. So we go back to the theory we just considered, which is large N UN Yang-Mills, and we add some probe fermions on top of this, which we can do because we're in the large N limit. And we use these probe fermions will allow us to discuss chiral symmetry, which has this condensate of the quarks as its order parameter. And so we know that the confined phase has center symmetry but broken chiral symmetry, and the deconfined phase has chiral symmetry but broken center symmetry. So we would conjecture that the partial phase might have both of these broken. So that's the conjecture we want to test. So the way we'll test it is by first finding where the transition occurs between partially confined and the deconfined phase, so where the gross Witten-Warrior point is. And we find that it occurs around at the given temperature that we're looking at, around P equals 0.35. So that's a number to remember. We then want to see whether chiral symmetry breaking coincides with this value of P equals 0.35. And if it does, that would be strong evidence for our hypothesis. So we do this by raising P and checking to see whether chiral symmetry is restored, and we keep raising it. And then we find that it's restored at the same point as the transition. So that's evidence for our conjecture. The way we do this in practice is by looking at the eigenvalue density of the Dirac fermions, and there's the Banks-Kasher relation, which I won't go into now, but which associates the order parameter for chiral symmetry with the density of the eigenvalues with zero value. And you can see that when the green value is P equals 0.35, where we expect the transition to be, and the behavior of this order parameter changes there. So this is what we can conclude for this theory, that we can characterize the partial phase by having both broken center and chiral symmetry. So this is the summary for this large N UN Yang-Mills theory that we've explored. It has this global symmetry breaking signature, and it has a linear potential in the subsector. Now we're looking at a second system, which is SUN supersymmetric Yang-Mills, N equals 1 super Yang-Mills, which has been deformed slightly in a way that I'll explain soon next. And we place it on R3 equals S1, and we also have the theta vacuum value of pi. So the advantages of this is that we can finally start talking about finite N with this system. It gives a cleaner global symmetry result. The deconfinement transition happens at weak coupling, and it's continuously connected to pure Yang-Mills. I'll explain that just now. So by deforming super Yang-Mills, what we mean is that the a small fermion mass. There's a small mass given to the fermions which breaks supersymmetry. So this is the action. There's the gauge kinetic term, the theta term, which is topological, the fermion kinetic term, and then there's the fermion mass. So in the supersymmetric theory, this term doesn't exist, and then we provide a small mass to deform the theory. And this was first introduced by, investigated by Poppet, Schaefer, and Unzel in these papers. Chen and his company looked at confinement and deconfinement, and there's a nice review by Poppets, which was out last year. And this is the phase diagram. So when the radius is small, then we're at weak coupling, and that's in this region here. And we can investigate this deconfinement transition analytically. And this is when the mass is 0, then we're in the completely supersymmetric theory, which is why this area is easy to control and investigate. But when we take the fermion mass to be infinite, then it decouples and we recover pure Yang-Mills. And it's conjectured that this transition is continuously connected in these parameters. So we'll probably learn about pure Yang-Mills by investigating this area. So in this case, instead of chiral symmetry, we're looking at CP symmetry, and having theta equals pi allows us to have CP symmetry in this theory, in the Lagrangian. But so the confined phase has center symmetry but broken CP. The deconfined phase has CP symmetry but broken center. And there's also an argument in this famous paper which one of these must always be broken. And so by anomaly matching arguments and this, then we would conjecture that the partial phase has both these symmetries broken. So we can do lots of manipulations on this action to make it simpler. The physics is that it reduces to this matrix model. And there's a term here which comes from combining two of these monopole operators M. And these create a bound state called bions, which have encourage confinement. But there's also monopoles which encourage deconfinement. And I will skip the details. But our procedure will be like before. First, we find this partial saddle. And second, we check symmetries at the Grossman-Wodja transition. So we find the partial saddle by solving the equations, and we can do this semi-analytically. So Chen and his collaborators before found this confined and deconfined saddles, but what we found is this partial saddle. So this interpolates between the deconfined and the confined saddle, and you get this typical swallow's tail pattern. So this is suggests that we find the correct saddle describing the partial phase. And this was at large n, and we can do the same at finite n. So this is for n equals 30. We again find a saddle tail solution. The deconfined and partial phase get very close around here. So this shows a log of the difference of the free energy, and you can see how they get very close together. So this will be the transition point, which we take in our units to be around 32.2. So that's a number to remember for the next few slides. So this y-axis measures something akin to the value of the eigenvalue density at plus or minus pi, and we can see its behavior changes at 32.2. So that suggests that this is a finite n analog of the Gross-Witten-Wodja transition. And second, we'll check to see whether the CP symmetry breaks at this point. So this y-axis is the order parameter for CP symmetry. And with the CP, we see that CP is broken in the partial phase, and it ceases to be broken in the deconfined phase. So in these finite n values, finite n cases, you can see that it smoothly goes to 0 CP breaking as we approach the deconfined phase. So again, we can see very clearly that CP breaking coincides with the beginning of the partially confined phase. So that leads us to conclude that having broken center and CP symmetry is a signature of the partially confined phase. And so we emphasize that global symmetries can be used to characterize partial confinement at finite n. So finally, we can talk about partial confinement at finite n, and we'll apply that in this special case here, which is some investigations which Chen and his collaborators did on SU2. So they looked at stable saddles, and they found that in between the deconfined and the confined phase, there was a mysterious phase, which was characterized by having both CP and center broken, and they didn't have an explanation for this phase, and they described it as exotic. But our suggestion would be that it's related to the partial phase, because it has the same global symmetry breaking pattern. But the difference being that for all other values of n, you get an unstable saddle, but for SU2 it looks like this, and that's the difference. So finally, I'll just say a couple of things about holography and QCD. This is the phase diagram at zero density for the quark-gluon plasma, and it's not well understood, and there's a lot of investigation going on into this crossover region, which is either a crossover or a phase transition. Understanding this diagram is relevant for cosmological history, as I explained in the introduction, and in colliders like RIC or Alice, and at high density it's relevant for the cause of neutron stars too. And our question is, does the partial phase existing in this quark-gluon plasma, and if so, is it stable? We want to know whether the crossover is a true transition or not, and whether chiral symmetry breaking coincides with the onset of partial confinement and the gross Witten-Wodjier point in this in QCD and the quark-gluon plasma. Next, I'll say a couple of things about holography. So this is the phase diagram for a black hole in ADS 5 cross S5, which is dual to n equals 4 CPMLs on S3. And is well known that the large black hole corresponds to the deconfined phase, and the string gas corresponds to the confined phase. But it's unknown what the small black hole corresponds to in the field theory. But if we compare against this diagram, then we would naturally conjecture that perhaps the small black hole corresponds to the partial confinement. And there's a similar conjecture in M theory, where the 11-dimensional Schwarzschild black hole be dual to partial confinement in D0 matrix model. So related to that question would be, where is the gross Witten-Wodjier transition in holography in the phase diagram of black holes? So if we are right that this is the partially confined phase, then we would expect to find it here. But there are other researchers who think that it will be in this Horowitz-Porchinski point, as described by these papers here. And so that would be an open question. So in summary, these are all the things that we've looked at related to partial confinement. We have the linear potential in the confined sector, global symmetries and order parameters, its relationship to holography and the quark gluon plasma, and the explanation of this mysterious SU2 phase. And I have some open questions remaining, which is it does the partial phase really exist as a stable phase in the quark gluon plasma? What would the bound states and dynamics of QCD and the quark gluon plasma look like in this case? Does the partial phase coincide with chiral symmetry breaking? And what would be its signature in a collider? And questions in holography. So what are the precise details of the mapping between the partial phase and the holographic jewel? And where is the gross wooden Wadya point? Okay, so that's all I had to say. Thank you very much for listening.
Yeah, thank you. Is Jyotirmay there? Yeah, I think. Yeah. Yes. So you're a student of Masanori, is it?
Yes, and